my name is Grady King. This week we're going to go over drivetrains, which is sort of just an extension of what we learned last week with how to move a motor. A drivetrain is 2 or more motors. Typically you have 4. Actually legally the maximum you can have is 4 now. And they are what makes it move. So it's like a car. It's the most important part of it. You can't really do much until you can move around. So that's what we're going to be doing. And there's a few terms here that we'll go over later, like tank, arcade, and some autonomous. But yeah. Oh yeah, so what is a drivetrain? The most important system on the robot. Here we have an example of a 6-wheel drivetrain. So you can see there's 6 wheels. And it's just 2 parallel lines on the bottom of the robot. And that's similar to this robot over here. This is Marvin 13. We used it in 2020, and obviously the season got canceled, but pretty good robot, and it has 6 wheels. There's other drivetrains. This is an example of Metronome, and it's kind of unique in that you see there's 4 wheels, but you can actually move side to side through a sort of series of movements by the wheels, which is, yeah, it's much more common in FTC because it's relatively simple. It used to be kind of common, but now all of us are moving more towards Swerve. Swerve is something that's a bit more advanced. It is super duper useful and really worth investing in, but we'll be going over it much later because it's kind of complex. But that's in general what the most common drivetrains are. Our goal today is to have that robot driving around with Java code. So the first thing we're going to do is actually power on the robot. We're going to be mostly working with this robot. So I'm just going to power it on. And so we're kind of going to do the first thing that you do when you're trying to make a subsystem move in a robot is look at the motors that are involved. On this drivetrain, it's not unique, but it's sort of something that's counterintuitive. These front 3 wheels are controlled by 2 motors, not 1. And the same with the other side. You could just make a drivetrain with 1 motor on each side that controls the 3 wheels, but that's not really as powerful. And like with this robot being like 100 pounds, it wouldn't really move very fast. So in general, using 2 motors per side is the general standard. So the first thing we're going to do is connect to it just like we would connect to this test bench. So I'm just going to do that through the same USB-B cable that we did before. So what I'm going to be looking for is which motors we're going to control. Like last week, you need to know the ID of the motor before you actually try to do anything. Luckily, it's actually labeled on this robot. On the right side, we have 4 and 5. And on the left side, we have 6 and 7. And so we can look at that in Phoenix Tuner and just confirm that those are the correct motors. So I'm just going to go into Phoenix Tuner. Oh, and I already have it open. And you can see we have all these motors here. Here's 4, and that's one of the right ones, and 5. And then we have 6 and 7. If you were just doing 1 motor per side, we could just tell it to move forward, but what we have to do is, because they're mechanically linked, we have to tell both of them to move at the same time, and that's something that's called a master-follower sort of thing, and I have a slide about that. So what's kind of happening is, you can see this sort of example where there's this shaft coming out on both sides, and then there's a gear in the middle, and there's 1 shaft that comes out. And that's kind of what we have here. is that the two motors control one side. And they're mechanically linked with gears. And so if we tell both of the motors to move at the same time, then they won't counteract each other, and they'll actually like add their abilities together, which is super useful. And you can do this super easily in Java code by using this like master-follower relationship. So what you can actually do is you can tell one motor to follow the other, and you can tell the master controller to move, and the follower will do the exact same thing. So that's what we're going to kind of set up. And we can do this in code pretty easily. I'm going to start a robot project, and we can start setting up these motors and kind of show what's going on. So I'm going to do the same thing that we did before, opening the WPI lib palette and creating a new project. And it's going to be the same type that we did before. So in here, it'll be template, Java, and we're going to do timed robot like we did before. We'll do command robot later, but timed is the most basic type. And I'm going to put this in the folder that I did last time and throw it in here. We're doing drivetrains.
Yippee.
Yippee.
Wait, you got this up here?
Yeah, I got this up here. So I'm just putting it in a folder here. It can be any folder you want, and I'm calling it training number 2. So that's what we're doing. And then the team number here. That's all you need. You can click generate project. And yes. So yes, I trust the authors. Just like last week, there's a few steps that we need to do to control one motor. The first one is installing the library. We're still communicating to the exact same motor that we were last week. And so we still need the same CTRE libraries that we were using last week. So if you recall last week, what we did is we went up to this button. If I can actually go to the button. Click the button. Go to Manage Vendor Libraries. Install new libraries. Install new. And then Phoenix 6. And this will, once again, this is to allow us to communicate to these specific types of motors. Because otherwise we wouldn't be able to communicate with them. I guess at this point, what we can do is sort of show the how these motors would move together, just using Phoenix Tuner. So one thing that you can do with Phoenix Tuner is run one motor just with Phoenix Tuner. And so I'm just going to kind of show this motor moving and kind of show like how, like what the behavior is. So I'm on the right master right now, which the right side of the robot is this side. So let's see. If we start moving motor number 4, theoretically, we want a forwards movement of the motor to be forwards on the robot. And so we can try it out, see what happens, and then go from there. So if we run master and hit enable, so we're going forwards, which if you imagine the floor being here, it would actually push the robot backwards. And that's typical of 6-wheel. And if we go to the follower,
Is Dalton in here? That's great. Okay.
He's downstairs in the. He's in the.
okay, now we're going the same direction. So yeah, if you don't have an inverted. So now that we're on factory defaults, so when they're connected them, when you connect them together like that, they both go the same direction. So yeah, we can go the same direction, same power, and they'll combine forces in effect. And we can also check this on the left side. And this is something that you want to do every time you're trying to make a subsystem, pretty much, is like checking what direction is it going, what's going on. And so now this is going to be the left side. So the left side, this would drive the robot forward. And so left side, we don't necessarily need to invert. And we can also check the follower, make sure it's also going the same direction. So yeah, same thing. So the left side, we don't need to invert. If we give a forward direction, the robot will move forward. On the right side, we need to invert it because a forward spin of the right motor will push the robot backwards, which is not what we want. We want to invert it. And that's what I was trying to show. Okay, so now that we have a plan, we can start doing it. So let's come in. So we need to. So here's our steps. We need to make these 4 motors. We need to invert the right side, and we need to make this relationship, and then we can tell them to move with code. So let's go into our robot, and hopefully this is looking reminiscent of last week. And so we already have the CTRE libraries in here. So we just need to start by making these 4 motors, and then we can go from there. So, and the way that we do that is you declare TalonFX variables. Remember, these motors are Falcon 500s, but they're controlled by a TalonFX. So we're going to make a TalonFX here. And you can see that actually it automatically imported at the top, which is pretty convenient. And so let's make the right drive master first. And so the right drive master, we can check here, is ID 4. So we can go ahead and put that into this constructor. And that's good. We can make our right drive follower. And that is going to be ID 5. Beeps. And then we're going to make our left side. So TalonFX, left drive master. And you could call these whatever you want. I'm just calling them something super descriptive so that I don't confuse them later. And it's going to be ID 6. And then the follower. Does anyone have any questions so far on?
I don't take drive extra one. There we go. There you go. There we go.
Okay, I think for the sake of time, I'm gonna keep going. The video will be posted pretty soon, so if you feel like you're falling behind, you'll be able to reference back. So now we have these 4 motors. The next thing that we need to do is set up this master-follower relationship. And this is pretty easy. There's a built-in function for it. And I forget what it is, so I'm going to check my other code. So the thing that you're going to do is call the follower and tell it to follow the master. And the way to do this, let's go with the right follower first. If you go right, drive follower. And what you're going to do is you can either type in follower and you'll see that there's this function called setControl. And that's kind of how I found it. And if you click here, then it'll give you this setControl function. what you're supposed to create is an object that is of type follower. It's kind of confusing in how it works, and it's sort of weird the first time that you see it, but every configuration is an object that you pass in. And you'll kind of see what I mean when I do it. So what you're going to type in is a new follower. And so this is a follower object that's getting passed into this function. And you can see that it's asking me for a master ID. And this ID is going to be what's up here. So we're just going to pass in 4. And the second thing that I asked for is this Boolean that is oppose master direction. And that's the thing that we were looking at before, is whether you want them to move the same direction or move different directions. What we found is that they should move the same direction, because both of them moving positive moved in the same direction. So we're going to pass in the master ID, and we're going to pass in false because we don't want it to oppose. And I know that's kind of confusing syntax. If this is happening where it's saying can't be resolved to a type, there's a way that you can go to quick fix here, and what I actually need to do is import follower. And so what it's going to do up here is it's going to import this follower type up here. But this is all that you need to do in order to set up this relationship. And it's kind of confusing syntax. The way that I found this syntax is through the documentation. And I can show where I found that. But that's all we need to do to set up the right side follower. We can do the same thing for the left side by just basically typing the same thing. So set control, and we're going to make a new follower. This time the master ID is going to be 6 instead of 4 because that's what's up here. And just like before, we don't want it to oppose the direction because we found that master and follower were in the same direction. And so now what we can do is we can just tell the master to move, and the follower will move in the exact same direction. And that means that both motors will contribute at the same time. And so now we have our relationship set up, and then we just need to tell the motors to move. And so I'm going to do this in periodic, just like before. And if you recall, the function to do this is to call set. So I'm going to let's just do the right side first. So let's do the right drive master. And I'm just going to set it to a speed, and we're just going to see if this works. So I'm just going to do that, and I'm just going to go ahead and deploy this just so we can see if we're actually doing what we think we're doing. I know I unconsciously did that, but what I did to actually take the code on here and put it onto the robot, I went up to the top right, hit this, and then hit deploy code. And that does everything for you. It compiles, or it builds the code, and then it puts it onto the robot. So now, theoretically, we should have only the right side moving at point 2 whenever I enable IntelliOp. And let's see if that is true. Oh, they're all following 4. Okay, that's my mistake.
Programming is all about doing things wrong the first time.
Exactly, yeah, doing things wrong the first time. It's really easy to do. And that's why I tried this, is because I wanted to test to see if I did it right, which obviously I didn't. And that's part of the fun of programming, is screwing up so many times that eventually you get it right.
And then wondering why it works. Can't forget that part.
Yeah, pretty much. Okay, so now I should be able to enable. Sweet. Okay, so now we just have the right side of the robot moving, and it's moving backward. I told it to move 20% forward, but it's moving backward. And this is what we found before, is that we need to actually invert this. And you can either do this by just telling it to move a negative value, or you can do a configuration to invert the entire motor. And that's what I'm going to do, because that way I can tell it to move a positive value, and it'll do what I want every time without me having to think about it. And this is going to be back in robot init. I'm going to go to the right master, and I think it's just set inverted, and I want this to be true. And I'm going to go ahead and also set left drive to not be inverted, because that's just good practice. So set inverted, and I'm going to set this to false, so that just to make sure that my left is always going to be uninverted and my right is always going to be inverted.
Like when we started, one of them was already inverted.
Yeah.
You didn't know, so
Yeah, I didn't know. So
to make sure.
that's the configuration sort of thing. And so now I'm going to actually now tell both of them to move at point 2, and theoretically they should both move the robot forward at the same speed. So let's try that. And it's the same sort of set. And let's deploy it. That was actually the sound of a configuration happening. So that was the inversion actually happening in real time. Let's go ahead and enable. And so now both sides are moving the robot forward. So if the wheels are moving backward, then the robot is moving forward. So that's exactly what I want. Awesome. Does anyone have any questions on what's happening right now? Is it all kind of making sense?
I mean, I got lost halfway through, but yeah.
That's why the video is there. You can go back, and if you have any questions, you can ask me once you go through it. All right. So this is great. I can move the robot at 20% forwards, but I want to be able to control it with a controller, because that would be actually useful. So let's go ahead and get that set up. Oh. Okay, so I guess I can start talking about how we're actually going to control this first. So the first thing that we're going to do is called tank drive. If you have seen a tank, basically how they control it is they have like two joysticks. The right side controls the right wheels, and the left side controls the left wheels. And so to go forward, you push both of them forward, and then to turn, you put them opposite. And this is super easy to code, because what we can do is we can just take the value of the left stick and tell the left side to move at that speed, and we can take the right stick and tell the right side to move at that speed. And so it's super simple to code. And so that's what we're going to do first. And I guess we can go ahead and get started on that, because we kind of know how to use a controller from last week. So let's go ahead and do that. So once again, the first thing that we need to do before we get the values from the controller is we need to make the variable of the controller. So we're going to do that up here. Just like the motors, we need a controller variable. And so, like we did last week, thank you, Sean, we're going to type in Xbox controller, and I'm going to call it controller. It's going to be a new Xbox controller. The port, let's look at the port. So if we go into the driver station, you can see that I have an in port 0, you can see if I wiggle the sticks, the values are updating. So we're going to use port 0, which it already is. So that's good. And then all we need to do is use controller and then .get whatever you want. So we're going to go down here and just like before, inside this set function, I'm going to take controller and do .get. And so for the right side, we're going to use the right stick y. So get right y. And then for the left side, we're going to use controller .get left y. And we're going to go ahead and just deploy that and see what we get. And so we're going to go ahead and try it. And in theory, this should be good. So it's enable. So if I move my left stick, see it goes pretty fast. And if I move my right stick, it also goes pretty fast. One thing, and it's kind of hard to notice because you're not controlling it, but if I push my stick up, it's actually going the wrong direction. And the reason that that's happening is because these controllers are kind of weird in how they are structured. If you look in here, you can see what the output of the controller is. And if you hover over, you can see the values. And as I push the left axis up, you can actually see it goes negative, which is really weird. I don't know why they did that, but that's how it is. I actually want, when I push the stick up, I want it to go forward. So what you can do is basically just invert it.
Tell it to get the invert.
Yeah, do the invert. And it's the same thing with the right stick. When you push up, it goes negative. When you push down, it goes positive. Why is that? I have no idea. But basically, we can just put a negative sign, and that works. Do you want me to put it down on the ground and kind of show it driving around? All right. So let's enable. And this is
Controller drift.
This is controller drift.
Yeah, actually we had to deal with that in FLL. We had to make it so like it's basically the values were between like 10 and negative 10. They're 0.10, negative 0.10.
Yeah.
Controller drift.
Yeah.
Just go everywhere.
One thing that we can do is use a library for this, because there's something built in that will do this for us. If for those who aren't aware, a deadband is basically the stick doesn't always go to perfect 0. We can actually see where it's at right now. You can see the top stick is at 0.06 when it's just sitting here, and the bottom is at 0.07 when it's just sitting here. So actually a 0.1 deadband would make it so that it's not going to move now, but when I move it, you can see it goes past that 0.10. And then when I release it, it goes back. And this is something that you have to have on pretty much every robot because controllers aren't perfect. And that's why you end up buying new controllers because of controller drift.
As long as it's not Joy-Con, you'll be fine.
Is there a way to see your
The issue is that it won't always settle to the same value. So you can actually you can see it settle to 0.1, and then 0.8, and then 0.6, 0.8, 0.7. So the issue is that you can't rely on a 0 actually working because it's like a range that it could possibly stop at, which kind of sucks. Yeah, it is annoying.
Normally new ones go below 0.05 like consistently, but these ones are kind of old. So.
Yeah, these ones are kind of old, so it'll take a while. But what we can do is use something called a DifferentialDrive, and that's sort of an object where you pass in 2 motors, and it'll kind of do this for you. This is relatively simple to set up. And we can also do the other forms of drive pretty quickly, which I need to do in the next 5 minutes because we're getting close to 8 p.m. And so the way that you would do this is create a differential drive object. You see there. And I'm just going to call this drivetrain. So I'm going to make a new differential drive. And what it's asking for are 2 motor controllers. And so what I'm going to do is I'm going to pass in the left master and the right master. So it's tight, and so first it's asking for the left one, so we'll pass in the left. And then the second one, it was asking for the right, so we'll pass in the right. And so the effect of this is we can, instead of calling on these individual motors, we can call on the drivetrain itself, and it'll control the motors from there. So it's like sort of a level of abstraction. And that's kind of what you end up doing in programming. So let's go to periodic, and instead of calling these set things, what we can do is we can call the drivetrain, and you can see that there is a few different types, and we want tank drive. And it's asking for a left speed and a right speed, and this is just going to be what we had from the controllers. And so it'll be controller.get left y. Oops. And remember that we had to negate it last time, and we're going to have to do that again this time. And then also negative controller get right y. To create the deadband that you were talking about, we can do that in robot init. It's just another sort of function that you call in the drivetrain. So you can do in robot init dot I think it's something deadband, set deadband, and we're gonna do 0.1 because in general it reset to something less than 0.1. So between 0.1 and negative 0.1, it'll just tell the motors to not move at all, and then outside of that it'll move. And so we should just be able to start this. And then hopefully it shouldn't go crazy.
I mean, you shouldn't. We have this step band in there. Just in case.
Just so I don't rip the cord.
Looks like you're computer.
And so you can see that we're within 0.1 on each of these, so theoretically it shouldn't move right now if I enable. Nice. So I'm going to move just the right side. And you can see that it's sort of like the left side is kind of dragging and the right side is moving. You can see it's kind of doing that. If I wanted to spin in place, then I'd move the right side forward and the left side backward. So kind of like this. And then the other way, like that. Sorry about that. And if I wanted to move directly forward or backward, I'd have to move both of them backward. Just like that. That's kind of frustrating though. Because what if I wanted to, go really fast? It'd be really hard. So I'm going to very quickly go over arcade drive. Arcade drive is more of what you'd expect. So one stick controls everything going forward or backward. The other stick controls rotating the entire robot. And this is more like, I don't know, an RC car or something like that, where, though different from an RC car, it can actually spin in place. I mean, I can kind of show how that works. And the only thing that we really need to do is, instead of calling tank drive, we're just going to call arcade drive instead. And so you can see how this kind of abstraction makes it really easy. And so you can see it's asking for a speed and a rotation. The speed is going to be my left Y stick. Rotation is going to be the right X stick. So controller.get left Y. And remember, we have to invert that. And that's also C what the X is actually doing. So as I move it right, it goes to 1. As I move it to left, it goes to -1. So actually we don't need to invert it because 1 should be a clockwise and a -1 should be left. So we don't actually have to invert that. Yeah, we are almost done. And so now this should be a lot easier to drive. And you can see why I kind of created these levels of abstraction is because it's super easy to change stuff out now because we have this one drivetrain. So now, if I enable, if I move the left stick back, it moves perfectly back. If I move the right stick or the left stick up, it moves perfectly forward. And then if I move, oh, I did left X. I need to do right X. Back forward. Yeah. Right. Beautiful. And now, so now I can like pretty easily control it, and that you know I can move forward as fast as I want, and then I can you know rotate where I want. And that's Arcade Drive. Arcade Drive is probably the most common way that people control these sort of 6-wheel robots. I guess that's going to be kind of it. I wanted to go over more, but obviously it's not going to happen. So thank you for listening. I don't think I'll have a challenge because we didn't go through everything. But we can go over a little bit more next time. Yeah. Thank you.
Yeah, it's back. I'm pretty sure this is backwards.
There we go. See ya. Why is it inverted? Thanks.
Like positive is
Why is positive?
is counterclockwise.
Did they do like a?
Well, I think generally like convention is positive is counterclockwise.
Yeah.
In like physics and stuff.
Physics.
Yeah.
Yeah, the right hand rule. Whatever.